we left off on rotational transitions. And where I left off last time was I just kind of briefly mentioned that we can use a rotational spectra as a molecular thermometer. And that's due to the population of states. So recall in the Boltzmann distribution, right, the number of molecules in state J divided by the total number of molecules, right, for the rotations is going to go 2J plus 1 for the degeneracy, of course, times e to the negative beta times the energy of a rotation, J, okay? And so when we think about it, why this is a molecular thermometer is because the number of molecules in state J will be a function of temperature. And the number of molecules in state J is going to be given by the intensity of that particular peak, right? So I think, right, recall that we labeled all of these transitions before, right, as we were discussing them. We recognized this very first peak was the 0 to 1, and then the 1 to 2, and the 2 to 3, and so on. Well, based on the temperature of this sample, there will already be a certain population of molecules in those states, and thus our rotational spectra will be a good indicator of the temperature of our sample. So it can be shown from this Boltzmann population that the J max value is approximately T divided by 2 times theta R, and theta R is the rotational temperature, and I'll show you that equation soon here, and minus 1/2, okay? And theta R, so this is known as rotational temperature, and in the absence of any molecular translations or vibrations, the temperature of a sample of molecules will be based on the molecule's rotational energy. And so typically rotational temperatures are very cold, extremely cold, a few Kelvin. Because like I said, in the absence of any translations or vibrations, the only thing left is really the molecules rotating, okay? And really, I suppose I should say in the absence of any vibrations or electronic transitions, because even at a few Kelvin, molecules will still translate. So they will have some translational temperature and some rotational temperature. Apologies for that mix-up. So the rotational temperature is given as just simply B divided by K Boltzmann, right? Where we recognize B, that's our rotational constant, okay? In terms of joules, right? And we recognize that K Boltzmann is joule per Kelvin, so 1 over Kelvin gives us a Kelvin, okay? And so now this equation is approximate and really only works best for, so this is the equation for one, linear rotors. And 2, really this equation only works best at higher temperatures. And I'm going to demonstrate that with my, my Mathematica file here on rotational partition functions. So, so the intensity of transitions will be proportional to the temperature of the molecule, the population of states. But also this equation right here, so this is given the expectation value for the rotational dipole moment operator, okay? So just like we've been talking before, the intensity of a spectroscopic transition will also be proportional to the dipole moment transition operator value, okay, the expectation value. So the larger a dipole moment is, the more intense its peak will be, okay? So there's really 2 factors that affect a microwave rotational spectrum: the temperature and the dipole moments created, okay? So here I want to switch over to my Mathematica file, and you can see here that I've got the molecular partition function, the rotational partition function Q. I've also got this dipole moment equation put in here. And I'm just making a simulated spectra by assuming that the intensity, the Y values, are just the partition function multiplied by the expectation value of the dipole moment operator. And of course, that is, a function of J. So as J changes, the dipole moment will also change. And so I'm just assuming that these are just a simple, one multiplied by the other, which is a pretty good assumption, actually. Okay, so here is a look at my spectrum. And on the x-axis, I'm just plotting the J value instead of, the frequency, right? And I've also got each of these values labeled. And so here you can see I'm starting out, in my manipulate feature, I'm starting at the rotational temperature, and this is for carbon monoxide. And you can see the rotational temperature for carbon monoxide is quite cold, 2.77 Kelvin. Really, really cold. So a sample of carbon monoxide, rotating in its ground state will have an energy of 2.77 Kelvin, okay? And so you can see the only state that's populated at that temperature is state number 1. If I were to zoom in on the scale, you could see that there is a teeny, tiny amount of population in state number 2 right there. Yeah, let's turn up that scale so we can maybe see that a little bit better. Right, so you can see some population in state 1, mostly all state 1, and a little bit in state 2. All right, so but now if I go back, I'm going to zoom out my scale so that we can see what happens when we increase the temperature. Okay, and so now as I increase the temperature steadily, let's hit around 40 Kelvin so we can compare to this spectrum we have here. And it moves quite slow because of those labels. Those added a lot of computational power. So you can see it looks fairly similar, although, this is predicting like state 3 is the most populated state. And we can see here, 0 to 1, 1 to 2, 2 to 3, 3 to 4. So that's not quite correct. And like I said, this equation is approximate. But if I go out to like 100 Kelvin, okay, you can see now maybe state 4 or 5 is the most populated state. And if I do this calculation of the J max, this is saying, yeah, state roughly 4. Okay, so it works better, this equation at higher temperatures. And now if I let this go and I'll push play on this thing and let it run through the different temperatures, you can see what happens as the temperature goes way up here. Lots and lots and lots of J levels become populated as we get to a really high temperature. Okay, so this is what allows a rotational spectra to be a molecular thermometer, which is really cool. Okay, so let's stop that. It moves quite slow on my computer here because of those labels. Okay, great. So now moving on. Oops, that's all the stuff that I talked about that was supposed to be on this slide. So right here is our full rotational partition function that, that I just walked you through, right? And just to make sure that we're clear on what all this stuff means, this whole chunk right here, HC times B tilde times J plus 1, all of that is given as this lowercase EJ, the energy of a rotational level, okay? Of a given rotational level, right? Depending on what the value of J is. And we remember that beta is 1 divided by K Boltzmann T, okay? So I wanted to show you a really, really cool application of microwave spectroscopy. And that's doing radio or microwave astronomy. So in this specifically would be microwave astronomy because we're probing the rotation of molecules. But this gives you a fantastic, fingerprint of molecules that might be in some distant celestial body, right? Such as the Orion Nebula, right? Millions, billions, trillions of miles away. And we know what's in it because of the microwave fingerprint, which is really, really cool. Okay, and so you can see there's loads and loads of simple molecules in that Orion Nebula. And specifically, you know, we've been using carbon monoxide as our example. Well, check it out. Here's some carbon monoxide. And then here's some more carbon monoxide. That's carbon 13 oxygen. Here's a carbon 18 oxygen. And let's see. And if we look at where this, what peak we're looking at here, this is around 230 gigahertz. If we back up for just 1 second to this table of values, check it out. That so 230 gigahertz, that's the same as 230,000 megahertz. Okay, so that was the 1 to 2 state. And so based on our simulation, we saw that at, you know, at 2.7 Kelvin, let's call it 3 Kelvin, there is some slight population of carbon monoxide. So we know at the minimum we're at 3 Kelvin or so in the sample, but oh, excuse me. But if we looked out, you know, further down the spectra and we saw another carbon monoxide peak, right, corresponding from the 2 to 3 transition, we could make some assumptions about the temperature of this nebula, which is so cool because it is trillions of miles away. And yet we can still get a good estimation of its temperature, which is really, really cool. And also we can see that the kind of molecules that we have here on planet Earth are the kind of molecules that exist everywhere, which hopefully you would have expected that. But the very first astronomers, right, the very first spectroscopic astronomers maybe didn't have an expectation of that. So I think it's just fantastically cool to see not only this distribution of small molecules in some distant celestial object, but also the fact that we can get a good estimate of its temperature. Okay, so I'm going to move past the rotational, and now I want to talk about why the width. Okay, why do these peaks have width? So we always talk about how in quantum mechanics, these transitions are exactly quantized, okay? So if they're exactly quantized, then why aren't they narrowly, you know, infinitely narrow is what I should say, right? A single peak, right, with no width. Why do they have some width? Well, as you might guess, it has to do with the temperature, okay? And more formally, so this is what we call line widths. So this is a random, you know, section out of chapter 9.6. Apologies for the different orders. But there's two main effects contributing to why spectra actually have width. This Doppler broadening is only relevant for gases, because if you recall, the Doppler effect is the change in frequency of an object as it's traveling away or to an observer. And you've all observed this all the time, right? The classic example is like the ambulance or the police car, right? That's driving by you, right? You can hear the frequency of the siren change as it's approaching you and then as it's receding from you, right? So that's due to the Doppler effect. I'm not going to spend a whole lot of time going through these equations. The main thing that I want to get into and point out is all of these equations lead to a width. So that delta lambda, right, that is the spread in lambda. So I'll note it on this figure here, right? So if I look at the width of this, that is my delta lambda, okay? Because, right, we recognize, or here this is, excuse me, delta frequency on this graph. I'll label that appropriately, right? So we could think of it, though, as a delta lambda. We could think of it as a delta frequency. We could think of it as a delta energy, right? It's some width of that otherwise would be, you know, infinitely sharp, right? This would be our infinitely sharp peak, okay? So, and you can see there's definitely some Boltzmann stuff going on there, right, with the 2kT. And the important thing to note, as you might expect, right, the colder a molecule is, the sharper its peaks are. And that's due to its random, chaotic Brownian motion, right? Whether it's moving towards the observer, and in this case, the observer is the spectrometer, right? So if we draw like our detector right here, okay, and I'm passing light through my sample and to my detector, you know, I could have molecules moving away from my detector and absorbing this light. I could have molecules moving towards my detector, right? And of course, in a random sample of gases, we'll have all angles in between, right? It'll be moving chaotically. So this owes to, at the very least with gases, in particular microwave spectroscopy, as well as gases in infrared spectroscopy, having an actual width, okay? So another factor, and this affects all phases, okay? And most importantly, the high energy transitions are most affected by lifetime broadening. And what we mean here by lifetime broadening is the amount of time a state spends in that upper lying level, okay? So if we think about this like an electronic level, for example, where I've got, I'll just use n to make this simple. Let's say we've got n equals 2, n equals 1, and we promote some electron to this state, okay? If we could keep track in time, so I'll say like I'll use, let's say n of state 2, right? If we could keep track of this molecule, the population of molecules in state 2 over time, we would see that it follows a first order decay. So all excited states decay via a first order process. And so from that first order process, we can get tau, the lifetime, which hopefully you remember from your kinetics. The lifetime of any first order process is just 1 over the rate constant for that process, okay? And so now the broadening, and so you can see here this is given as delta E, so the width of the transition is just simply h bar divided by its lifetime. And I've got some more calculations here just to kind of demonstrate this point. And so a typical lifetime for an electronic state, so let's write that down. So for the electronic levels, a typical lifetime is about 10 to the minus 8 seconds. Now, the amount of time it takes to access that state is really fast. It's actually like an attosecond. That's like 10 to the minus 18 seconds. But it will live in that state for, you know, approaching a nanosecond, or really like 10 nanoseconds, okay? So it'll take about 10 nanoseconds for all of the molecules to decay back down to the ground state. And of course, they're releasing light in that process. And the light that is released in that process will have some breadth. It will be, it'll have some uncertainty to it based on this lifetime, okay? And so here you can see I've calculated that. So I've said my delta E is just h bar, right, which is h divided by 2 pi times tau. And I have converted that. Well, actually, I ended up deleting that because it was confusing to do delta lambda. So let's just do it as delta E. And then this factor right here converts it into an electron volt, just so we can kind of get an idea of easy numbers to use. And you notice here, when I make the lifetime 10 to the minus 8 seconds, there is an uncertainty in that transition, a width, of about 10 to the minus 8 electron volts. That's pretty small in the grand scheme of things, okay? Pretty small. But what happens if maybe I increase that lifetime by, you know, a factor of 10? So now you can see that that width is getting bigger, right? So and if I go to 10 to the minus 10 for my lifetime. So now I'm making it even shorter, a really fast lifetime. You can see now that width, right, because of this inverse relationship, that width is getting bigger. So the faster our molecules decay, the more uncertainty there is in where its peak should appear, all right? Now, what about microwave? Rotationals. Okay. Lifetimes for microwave transitions are on the order of 10 to the 3 seconds. That is a humongous amount of time. That's like 20 minutes, you guys. That is a huge amount of time. And so now when you think about that one, if we put in 10 to the 3, and look at this. This is still in electron volts. 10 to the minus 19 electron volt uncertainty. Okay? And so what's going on here is the longer a state spends in that lifetime, the more certain it is. We know that it's in that lifetime, okay? And it stays there for a long time. So there's less uncertainty about its, where its position occurs on the energy scale. But the faster something is, the more chaotic it is, the more that it goes to these excitations and then emissions, and excitations and emissions, the bigger the width is that we have. Okay. So this was a pretty short lecture, and I think that's a pretty good place to wrap it up, because where we're going next is molecular vibrations. All right. I'll see you in the discussion of vibrational spectroscopy.